Howdy, Psych92 here, and in this episode we're going to be setting up the peripherals for our digital oscillator section. We're going to begin by talking about some basic digital audio concepts, then we're going to move on to building the circuits for our peripherals. Then we're going to go ahead and program the Arduino to interact with the peripherals, and then finally we're going to validate the output by testing the audio output and then also echoing MIDI messages. Everything you need to build the circuits is going to be in the video description below. As I said in the last episode, we're going to be using an Arduino Uno as the digital oscillator section of BitBase. It is severely limited in processing power and I/O, but we're going to be able to squeeze just enough of what we need out of it. We are going to have to add some external circuitry, however. Before we get into the technical aspects of the Arduino Uno and what we're going to need from it, first let's run through the basics of digital audio as it pertains to our project. The goal of the Arduino Uno in our project is going to be to create analog waveforms from digital samples whose frequency is dependent on the incoming MIDI data. So of course this means we can use any standard MIDI keyboard to play musical notes on our synth. The Arduino Uno is going to be running at a predefined sample rate, meaning that it's going to output an analog value after every completed period. So let's take a look at that graphically. Alright, so here we have our Arduino Uno and it's running at 16 kilohertz, that's the sample rate, and then basically what that means is that 16,000 times per second it's going to send a binary value to our DAC, and our DAC is our digital to analog converter. It takes in this binary value and then it outputs an analog voltage. So as you can see here, this is 5 volts, this is 0 volts. Alright, so let's say that each of these lines here is a completed period. For 16 kilohertz, the period is going to be 0.065 milliseconds. So each of these is 0.065 milliseconds. So let's say that we wanted to output this real wave. That means that the Arduino Uno is going to need to send binary values to the DAC that correspond to these voltages here. So we're going to need to send, like I said, binary values to the DAC, and it's going to output these right here, because remember we can only output a sample each period, and then that's going to approximate this wave. Now if we wanted to bring this wave down by an octave, what we would do is we could double these. So have this one output twice, have this one output twice, and so on. And if we wanted to increase it by an octave, we could skip this this value here, skip this one here, and basically go do each other sample. So I know that was a super brief description of how digital audio works, but we are going to be using these concepts to build BitBase. So if there's anything you're unsure of about digital audio, you might want to brush up and just Google some things. So now that that's out of the way, let's take a look at the datasheet for the Atmega 328P, which is the microcontroller used by the Arduino Uno. Now, if I were just starting a project involving a microcontroller, the first thing I'd want to do is pick one that suits the needs of the project. And the needs of this project are audio input and output. And the first thing I notice here is that we have a 16-bit timer counter with an interrupt, and that's going to be used to set our sample rate. So that's good there. If I'm looking here, I see that we don't have an internal DAC, which that's bad because we need to output a voltage. So thankfully it does have SPI and I2C, so we're going to use that to set up an external DAC. Also notice that we have USART connection here, which is going to be important because we need MIDI input and output, and that's the communication protocol that DIN MIDI uses. So this is essentially going to be our digital oscillator section. We're going to have a MIDI input and output, so we're going to have a device send MIDI input to the Arduino through this DIN connector here. Then we're going to have the Arduino send some binary values, which is going to be our waveform, our digital waveform, to the DAC, and that's going to output our analog waveform. And then finally that's going to go to a filter and amplifier section. Alright, so I don't want to harp on this for too long, but it is a subject worth at least briefly visiting, so I'm going to show you how I would find the peripherals to work with my project. Specifically, I'm going to be focusing on how I would find the correct DAC to use. So we'll go to products here, and we're looking for an integrated circuit, and specifically a DAC. And remember that we're looking for either an SPI or I2C DAC. So those are the communication protocols. So you can go here, select SPI, and then also for the package we're going to go with 8-dip, which means it has the protruding pins, so we don't have to solder them in place. You can use a breadboard. So searching through these, really any of these would be fine here, but I'm actually going to go with the MCP4921 since I happen to have one already on hand. And then also I'm going to download the data sheet, which I happen to already have open right here. But really, if I was buying this for the first time, I would read the data sheet first so that I knew what I was getting. And it's also going to be important later for programming the communication interface and also for just setting up the circuit even. So now that we have all that basic information out of the way, let's get to actually building the circuit. To design the circuit, I'm going to be using Fritzing, which is a free and open source schematic and PCB editor. So the first goal is going to be outputting voltage via the DAC. So first we're going to drop in the Arduino Uno model, and then we're going to drop in this generic 8-pin DIP package, which will be our DAC. So let's pull up the data sheet and see how this needs to be connected. So if we go up here, we can see all the different pins of the package. Let's first just start off by getting the power and ground pins. It's all set up. So pin 1 here is going to be the power pin, and pin 7 here is going to be ground. Next we'll set up the serial pins, which is going to be how the Arduino talks to the DAC. If we see here, we have the chip select pin, the serial clock pin, and SDI, which is serial data in. On the Arduino, that's going to be master out, which is CDI, or SDI, I mean. And then we're going to have S clock, which is the serial clock. Finally, we're going to use our chip select pin, which is going to be pin 10 here. So if we look at the data sheet here, we see that VREF is essentially going to be the maximum voltage output. So we're going to want that to be 5 volts, so let's connect that again to 5 volts. Our last pin that we have to connect here is this LDAC pin. Let's check out what it does. So looking at the data sheet here, we see that the LDAC pin transfers the input latch registers to the DAC registers. So it can also just be tied low if transfer on the rising edge of the chip select is desired, which is exactly what we want. So let's just tie it low. So finally, we're going to add what's called a decoupling capacitor. And basically what that is it's going to isolate this circuit here from noise that might be going on in other parts of the circuit. And it's generally a good practice to add decoupling capacitors, sometimes even of multiple different values, to any IC in your circuit, and to also place them as close as possible to that IC. So here is the finished schematic on the breadboard. So remember, all these files are going to be on the GitHub page linked below, so it should be really easy to build the circuit. Now that we have our DAC all set up, let's write the setup code so that we can actually be able to use it. So this is the Arduino IDE, and basically this setup and loop, these blocks here are going to be equivalent to this in C. So normally this is where your setup code would go. Let's just set up, and then we'd have a while loop that runs infinitely, and that's basically how embedded C works. So think of your setup code as being right here, and then your loop code as being in this infinite loop. So the first thing that we're going to do is we're going to go ahead and we're going to define our sample rate. So this is a really low sample rate for audio, and it does create some serious aliasing issues, but this is just about the limit of what the Atmega 328 can handle after we add the rest of our code, and we'll see that this is just enough for what we need later. And next we're going to initialize timer 1, which is the 16-bit timer that we're using to generate an interrupt 16,000 times per second so that we can output audio from that interrupt. And you'll see what I mean in a second here. We'll call this function timer1 initialize. We'll have to take a look at the datasheet to see exactly how to do this. As you can see, there's a lot to read here, and if you really want to know what's going on, you should actually read this, but I'll go over the most important bits. So you can read more into these registers, but basically what I'm going to be doing here is just setting up normal port operation. Then we're going to set clear timer on compare mode, which basically this makes the timer increment until it reaches a certain value, and then it clears itself, and then it repeats. And this is how we're going to set up basic sampling, because when it does reach that point, it sets off an interrupt. And we're also going to set the prescaler to be clock rate divided by 1, which basically means no prescaling, and prescaling reduces the clock rate for the timer, which we really don't want. Again, I know this is a little esoteric here, but you can look in the datasheet at the registers. I'm just kind of explaining it as I go along. Also, if you don't really understand the code here as to what I'm doing with the bitwise operations, you might want to look into bitwise operations. Basically, I'm taking this 8-bit register and I'm inserting ones into specific places that act as flags that control how the system operates. The TCNT1 register and the OCR1A registers are the ones that are going to be compared. So the TCNT register is going to be the one that's incremented and then compared with the OCR1A register. So let's just begin by setting the TCNT register to 0 for now. So we really need to have an interrupt fired each time TCNT1 register matches the OCR1A register, so we can set this up with the TIMSK1 register. So like I was saying, in the datasheet here you can see that it gives a better description than I'm giving here probably of each of the registers. So this is the one that we just put a 1 in this place right here, which allows for output compare A match interrupt enable. So when this is written to 1, basically we can allow interrupts to be enabled. Finally, we need to set the OCR1A register to the right value so that we get the correct sample rate. And the formula is pretty easy to understand, and it's in the datasheet somewhere, but basically we take FCPU, which is the clock rate of the microcontroller is using, which for us happens to be 16 megahertz, then we divide that by the sample rate. So if we did that, the calculation would be 1,000, and then finally we subtract 1 since we're actually beginning at 0. So finally we have 999. And this should make sense intuitively because we're outputting a sample every 1,000 clock cycles, which would mean 16,000 times per second at a clock rate of 16 megahertz. Now hopefully all that made sense, but if it didn't, I encourage you to actually read the datasheet, which will give much better descriptions of all those registers that we're putting these values into. So now we're going to set up the Atmega 328P as an SPI master device, and we'll call this function SPI DAC master in it. First we'll set up the serial out pins as outputs in the data direction register. The digital and analog I/O pins on the Atmega 328P can be set up as inputs or outputs using this register. Next we're going to set pin B2, which is the chip select pin, to high since we're not immediately writing to the DAC. So looking at the datasheet here, we see that we're going to need to set the bits for SPI enable and then also the bit for master here, which sets it as a master device. So that function is done now. We're one step away from actually being able to use the DAC. So next we'll need a function that actually transmits SPI data. So looking at the datasheet here, we see that the chip select pin needs to be pulled low while we're sending data. So let's put that in our function. So we can also see here that 4 of these bits are going to be used for configuration and then 12 bits for data. So we're going to have to send 2 8-bit data packet. So first we'll set up the data packet 1, which holds our configuration bits. We're using 0B for binary here. We're going to want to write to our DAC register, so the most significant bit should be 0. We want our VREF pin to be unbuffered, so we're going to set the next bit to 0. We want the max output to be 1 times VREF, so the next bit should be 1. And finally we're going to want the analog output to be available, so we're going to write 1 to the next bit as well. And if you look at the datasheet here, we can see how the bits correspond there. Now data packet 1 needs to be 8 bits, so we're going to add 4 zeros to the end. And these 4 bits should be bits 11 through 8 of the 12-bit output data. We'll OR the input data bit shifted to the right by 8. It's also important to note that we need our input data to stay in the range of 0 to 4095, or else this operation will mess with our config bits. We could do this in a bitwise operation just to ensure this, and it's an additional operation that needs to be called each time we output audio, so we'll just make sure our output data fits in this range somewhere else in the code. So now that we have data packet 1, we'll send it by putting it in the SPDR register, which is the SPI data register, and we'll wait to ensure our transfer is completed. To wait for the transfer to complete, we're going to actually use a while loop here. Now this while loop basically waits for the SPIF flag or the SPI interrupt flag to be set to 1, indicating that the transfer is completed. Data packet 2 is just bits 7 through 0 of the input data, so we'll just use a mask to mask out the first 8 bits of the input data, and that'll give us our data packet 2. Then to send it, we're going to do the same thing we did with data packet 1. So now we have all the code we need to send SPI data. It's not exactly straightforward, is it? So with all that setup code out of the way, let's actually test our DAC by using a 320 Hz square wave and sending it out of the DAC. So how exactly can we do that? Well, first of all, remember that we're sampling at 16 kilohertz, so that means 16,000 samples per 1 second. And what our goal is we want to output a 320 Hertz waveform, which is 320 cycles per 1 second. I can't really spell here. So mathematically what we can do to get what we really want, which is how many samples per cycle do we need, we can go ahead and we can divide, which is the same thing as multiplying by the reciprocal. So 16,000 samples over 1 second times 320, or times, I'm sorry, 1 second over 320 cycles. And what we get if we multiply is we're going to actually end up with 50 samples over 1 cycle. So that's exactly what we need. We have our answer here in samples per cycle. So we need to output 50 samples per cycle to get our 320 hertz waveform. And basically what we're going to do to make that a square wave is that we're going to take 25 samples, make them high, 25 samples, make them low, and we'll output that to the DAC. So remember how earlier I was talking about that 16,000 times per second an interrupt is going to be fired? Well, we can write what's called an interrupt service routine, which is basically code that's run every time that interrupt is fired. And that's how we're going to output our audio. So first let's write our interrupt service routine, and we're going to do that by specifying a function called ISR, which has no return type and takes in an ISR vector as an argument. Since we're using timer1's compare feature, we're going to pass in timer1 comp a vect. We're also going to need a variable that we can use to determine if the output should be high or low. We're going to call it wave increment. Now notice that I'm using the volatile keyword, and it's kind of a good rule of thumb that any variable that's going to be read and written to in outside of mainline code, meaning like interrupts in this case, should be volatile. So basically it ensures that the variable isn't optimized in memory, which could create some discrepancies across different segments of code. So I know that's a really bad description, but look up embedded volatile keyword if you want to get a better understanding of why we need this in a lot of cases. So we're going to need an if-else statement to determine if the output should be high or low. If the wave increment is less than 25, we should output high and increment the wave increment. And if it's less than 49, we should output low and also increment the wave increment. And if it's above that, which in this case would be 49, we should output low and then also set the wave increment back to 0, and then which will basically loop that and output our 320 hertz wave. Finally, we're also going to need to add the functions timer1 initialize and SPI DAC master init to our setup. Notice I also put in CLI and SEI, which basically CLI disables interrupts and then SEI enables them. So we're just basically ensuring that nothing's going on while we're messing with interrupts. So I just realized that I forgot to make 2 of those functions void, but after that you should be able to compile it and then upload it to your Arduino, and you should be getting a 320 hertz square wave. So let's take a look at that on the oscilloscope and see if that's correct. So yep, that most certainly looks like a square wave. Let's see if the frequency is correct. So if I put my cursor on this, you probably not able to read it up there, but it says 320 hertz, so that is correct. We have our audio engine implemented, but to be able to actually play this with standard MIDI devices, we're going to need to implement MIDI input and output. So let's start by setting up the circuitry. Alright, so this is the complete MIDI 1.0 specification, which we're going to be using to look up the electrical specification. First, we're going to skip straight to the detailed specification, and then we're going to go to the hardware section. As you can see, we need 2 5-pin DIN MIDI connectors, 4 resistors, a diode, and an opto isolator. And we'll also notice that the opto isolator is the Sharp PC900, but since I have other opto isolators on hand and also the PC900 is discontinued, I'm going to be using the Sharp PC817. So this is going to change some of the resistor values, but I've determined them experimentally beforehand, so other than that, the schematic's going to be the same. So we're going to be building the MIDI in, which is this circuit here, and then also the MIDI out, which is this circuit here. So the from UART and the to UART pins detailed on the schematic are actually the TX and RX pins on the Arduino, which you can find right here. And let's begin by getting the opto isolator out. Thankfully, Fritzing has the Sharp PC817 in the part library. We're also going to need some MIDI connectors. We'll connect pin 5 of the MIDI in connector to the cathode of the internal LED of the opto isolator. We can then put a 180 ohm resistor between pin 4 of the MIDI in connector and pin 1 of the opto isolator. Then we'll put the diode on the schematic. And notice I'll be changing the resistor values from what was originally in the MIDI spec, and this is because I'm using a different opto isolator. I had to find these values out experimentally using my oscilloscope. Next, we'll put a 560 ohm resistor between 5 volts and pin 4 of the opto isolator. Then we'll connect pin 4 of the opto isolator to the RX pin of the Arduino. And then finally we're going to connect the emitter of the internal transistor to ground, and that's going to complete the MIDI input circuit. Now to the MIDI output circuit, which is a little bit simpler. We'll follow the MIDI spec and use 220 ohm resistors between 5 volts and TX. So I know that's a pretty sloppy schematic, but I'm going to try and clean it up a bit before sending it to the GitHub. Another thing that's important to note is that every time you're going to want to program this with USB, now that we have this MIDI input circuit set up, you're actually going to need to remove the RX pin before you program it. So now let's write the necessary setup code to allow for USART communication between our MIDI devices and our synth. Just like we did with Timer 1 and SPI, we're going to need to write an initialization function that sets up our USART configuration. We're also going to need to define our MIDI baud rate, which I happen to remember is 31,250 bits per second. Next thing we'll do is set up our USART baud rate register, or UBRR register. I'm not going to go into how this is derived, but if you have a look at the data sheet, you can see how it gives you the formula. So now I have to take this 16-bit UBRR value and put it into two 8-bit registers called UBRR 0H for high and UBRR 0L for low. We'll bit shift UBRR to the right by 8 and cast it as an 8-bit integer to get UBRR 0H, and we'll simply cast UBRR to an 8-bit integer to get UBRR 0L, which will truncate the integer. Next, we're going to need to set up USART to both receive and send data. We can do this through the USART control and status register. So let's take a look at that on the datasheet. So here's the register. We see that we're going to need this RX complete interrupt enable written to 1 so that we get an interrupt every time that we receive MIDI data. We're also going to want 1 on RX enable, which is just to enable the receiver, and then also enable transmitter. This next line here is going to set the size of the incoming data bits to 8 bits. So after we do this, USART will be all ready to send and receive MIDI data. You should note that I didn't talk about all the register values regarding USART, and that's because the initial values suited our purpose, but you really shouldn't assume this when working on other projects. In order to send MIDI data out, we're going to need a function that writes the data to the USART data register, and we're going to call that USART transmit. So we'll want the function to make sure the last transfer is complete, so we'll do this with a while loop that checks to see if the USART control and status register A has the USART data register empty flag written to it, which this happens every time a USART transmission is complete. To send the data, we'll put the data in the USART data register, and that's pretty much it, and then our transmit code's complete. So we've covered initializing and transmitting, so now we'll need to cover receiving MIDI data, and we'll do that in an interrupt which is fired every time MIDI data is sent to the device. Before we write the body of this function, let's define some structures that'll help us better comprehend MIDI events. Hopefully you have some experience with what MIDI messages look like, but in case you don't, we'll open up this summary. So our synth is only going to be concerned with note off events and note on events. And as you can see, they also have some other data in here as well, which is N for the channel, K is the note that is being pressed, and then V is the velocity. Since we're only recognizing these two different messages here, basically every event is going to have one status byte and 2 data bytes. Notice that the status bytes begin with 1 and the data bytes begin with 0. We'll define the first 4 bytes of note on and note off messages so we can use those later. Now, since both MIDI note on and MIDI note off messages consist of 1 status byte and 2 data bytes, we can define a structure that will help us better comprehend MIDI events in code. We'll make it volatile since it can be written to and read in places other than the mainline code, and we'll type def it so we don't need to write struct everywhere. We'll put the data in it, so 1 8-bit status byte and an array of 2 8-bit data bytes. It's pretty straightforward that we're going to have our interrupt writing to these MIDI event structs, but instead of just having one of them, which could be overwritten if another MIDI event is received before this one's processed, let's have a circular buffer of MIDI events so that that's significantly less likely to happen. First, we'll have to define a MIDI event buffer size so that we can change that as we see fit. We'll see how this works in a second, but it's also important to note that we'll be taking the main processing of the MIDI event out of the interrupt code and we'll be dumping it onto the main loop. And that's super important because our interrupt code needs to be lightning fast so that we don't experience any slowdown or even worse when MIDI data is received. Also, I just realized I forgot this. We'll need some other variables before writing to the body of the interrupt as well. First, we'll need the MIDI write index, which will keep track of the current position we're writing the MIDI event to in the circular buffer. Then we'll need the MIDI writing flag integer, which will determine if we're writing data bytes to the MIDI event, and if so, which data byte. We're going to initialize that to 255, which we're going to determine means that we're not writing data bytes. And then we're also going to make both of these volatile. So coming back to the interrupt code, let's start by getting the incoming data out of the USART data register. We can extract whether it's a note on or note off message by bit shifting the data to the right by 4. Now we'll set up our logic. If the MIDI message is a note on or off message, we'll write the status byte at the MIDI write index, and we'll also set the writing flag to 0, since the data after this will be the first data byte. Else if the MIDI writing flag is less than 1, then we'll write the first data byte at the MIDI write index and increment the MIDI writing flag. Else if the MIDI writing flag is less than 255, we write the second data byte at the MIDI write index. So there's an important concept in MIDI that we need to be aware of called running status. What this means is that if multiple notes are pressed at once, instead of sending several status bytes, the MIDI device will only send one status byte and then several data bytes, and that'll ignore their respective status bytes. So we have to be very careful to write code that will allow us to receive that data. Since we possibly won't be receiving the status byte to the next MIDI message, let's write the current status byte to the next MIDI write index. First we'll get the current status byte, then we'll get the next MIDI write index. Notice I'm using the modulo operator to make sure that the number wraps around the MIDI event buffer size. So since it's modulo 10, when the MIDI write index reaches 9, the next increment will actually be MIDI write index to 0 instead of 10. Now that we have our new MIDI write index, we'll write our current status byte to it. Finally, we'll set our MIDI writing flag to 0, just in case of running status. With that done, we've implemented our MIDI receive system. The system will write MIDI events to the MIDI event buffer. So let's verify that it worked by echoing MIDI messages. So this is our MIDI event buffer as it is now. We have this size of 10 buffer here, and we also have our MIDI write index. And basically it's going to write MIDI events to the buffer from 0 to 9, and then it's going to loop back to 0 since we're using that modulo operator. So in order to have our main loop process these MIDI events, we're also going to need a MIDI read index. And we're going to use a modulo operator just like that. So let's say that the MIDI write index reads 4 MIDI events. Our MIDI read index is going to start at 0, and in the main loop it's going to have to process the MIDI event and then increment, process the MIDI event and then increment until the MIDI read index equals the MIDI write index. So basically it's going to lag behind our MIDI write index, and then it's going to process up until that point. So that'll also wrap around. So basically it's just following the MIDI write index, and it's all done processing when both of these values are equal. So hopefully you understand how that works. Let's get to actually coding it. We'll start by initializing the MIDI read index variable. Since it's only going to exist in our main loop, we don't need to make it volatile. Now in the main loop we're going to set up that circular buffer code. While MIDI read index does not equal MIDI write index, increment MIDI read index. To echo the MIDI events, we're simply going to transmit the status byte and the data bytes sequentially using the USART transmit function. We also need to add the USART init function call to our setup, and that's pretty much all we need to do to validate our MIDI system. Now let's actually test it out. Okay, so I just noticed in the code when I'm incrementing the MIDI read index, I'm actually not using the modulo operator, which I need to do. So I changed that, and all the actual code is going to be on the GitHub page just in case there's any compiling errors. So to test out the MIDI echoing, what I'm going to do is I'm going to have my Roland Juno G send MIDI to the MIDI input of the bit bass. Then I'm going to have bit bass's MIDI out go to my audio interface, and I'll use it to play a soft synth on my computer. So as you can see, the orange chord is the Roland Juno G, and that's going to my audio interface here. And I'm using it to play the soft synth battery 4 here. So it's working. We officially have our audio engine and our MIDI engine working correctly. So we started this episode by talking about some basic digital audio concepts. Then we went ahead and set up our DAC and our audio engine, and we implemented that and then validated it. Then we did the same with our MIDI engine. We set it up and then we validated it. And in the next sequence, what we're going to do is we're going to start working on our actual synthesis engine. And what that's going to do is it's going to process those MIDI events that we have in our MIDI event buffer, and it's going to output waveform that is either a sine, square, triangle, or sawtooth wave, and it's going to output it at a specific frequency, which corresponds, of course, to the note that we're playing on our MIDI keyboard, for example. So hopefully this episode was presented well and helped you understand these concepts. If not, I'd love to hear your suggestions in the comments below, and I'll see you next time.